Okay, vamos a empezar. Good morning, everyone. It is a great pleasure to welcome you to the Advanced School Geometry in Quantum Physics. We are delighted to see many of you here in the auditorium, and we also warmly welcome those joining us through the YouTube transmission. Whether you're sitting here with us or following from afar, we are glad to have you as part of the school. The title of the school brings together two concepts, geometry and quantum physics, each of which already contains a whole universe of ideas. When they meet, they lead to some of the most beautiful and powerful structures in modern mathematical physics. Over the next couple of days, 4 speakers will guide us through different parts of this landscape in the form of mini courses. 3 of them are here with us in person, and 1 will join us remotely by Zoom. I would like to thank all 4 of them very sincerely for accepting our invitation and for the work they have put in preparing their lectures. I would also like to express my gratitude to the director of the Institute, Alfred Uren, and the academic secretary, Yuri Bonder, for supporting this event and making it possible for us to hold it here at the university. Many thanks also to Aline Guevara, who designed an exquisite poster and gave the school its unmistakable visual identity. I would like to thank my current and ex-students and postdocs, Luis Aragon, Ala Flores, Igor Vasquez, and Valentina Rascon, who have helped with many practical details. A special thanks to Valentina for preparing the webpage of the event and helping make the school accessible to participants and visitors. Finally, I would like to thank my co-organizers, John Martin, right now in Liège, but soon to join us in Oaxaca, and Eduardo Serrano and Sastiga, who is here with us, for their ideas, collaboration, and steady work throughout the preparation of the school. To all participants, thank you for being here. I hope these 2 days will be scientifically stimulating, useful, and enjoyable. A school is not only a sequence of lectures, it's also a meeting place. Welcome all to ICN. And with this, I would like to introduce Marek Kus, who will give the first mini course titled Symplectic and Algebraic Geometry of Quantum States, Part 1.
Thank you very much. It is really a pleasure and honor for me to lecture and here and in ICN. And I'm very glad to see that the audience is quite numerous. So this is really a challenge for me. And I thank you very much for coming. So the title of my talk, which is written here, is really about geometry in quantum physics. Let me start with the following remark. So usually we are taught that quantum mechanics is a linear theory. Better? Okay. I will try to avoid to put it on my ears, but okay. Okay, thank you. So, coming back to what I wanted to say, that quantum mechanics is a linear theory. It's indeed the field of battle, I would say, is a Hilbert space. It's a linear space. Then the equations governing the dynamics, quantum mechanical dynamics are linear, Schrödinger equation. But when we look a little bit closer, this is not longer true to the very end. And this is because of, so coming back to this linear theory. So because this is a linear theory at first sight, so it seems that, well, okay, so the natural tools offered to analyze quantum mechanics are offered by linear algebra or infinite dimensional by functional analysis. We will concentrate here on the finite dimensional Hilbert spaces just because this is the most common base for analysis in quantum information theory, where we consider spin systems or systems with finite number of degrees of energy levels and so on. So So this is really should be linear algebra. But as I mentioned, when you look a little bit closer, this is not true to the very end, just because we are also somehow restricted by the probabilistic interpretation of quantum mechanics. So in fact, which usually in physics we say, okay, that we have a state, pure state is a vector in a Hilbert space, but the vectors which are proportional to another describe the same state. Okay? So what does it mean, really, in mathematical language, is that we are considering not longer a Hilbert space as a space of states for a quantum mechanical system, but a projective space. And this when the geometry actually comes into play. Okay? So let me start from such a very short crash course in quantum mechanics, which would be rather vocabulary, okay, or the collection of symbols which I will use just to fix the notation, because these are probably the things which are quite known to everybody. So quantum states, general quantum states, are in fact operators acting on the Hilbert space, on this Hilbert space I mentioned at the very beginning, as the basis, mathematical basis of quantum mechanics. And moreover, these states should be these density matrices. Matrices are linear operators on the state, which are positive and have trace 1. Okay? As already mentioned, we will concentrate on the finite dimensional Hilbert spaces, so everything is more or less well defined here, trace and so on. Okay, so pure states, which correspond to, at this, I would say, algebraic level to vectors in Hilbert space, are rank 1 projectors. So projections on one-dimensional subspaces of this Hilbert space. So projectors, it means that if we apply twice the same operator, it is the same as applying it only once. Okay, nothing has changed. By the second application, this is clear that this is exactly the feature of a projection. So we will adopt this very popular Dirac notation concerning vectors and dual spaces. Okay, so this bracket notation. So by this cat, by the cats, we will denote the vectors in H and this linear forms, so linear operators acting on this Hilbert space by this brass. Okay. Okay, so the scalar product, this is very convenient notation because the scalar product in Hilbert space is just this bracket. Okay, so these pure states at the very can be identified with, as I told you, with points in the projective space. So these projectors actually look like that. Okay, so for a given vector, this projector looks like that. Okay, this is a shorthand notation. Also, I would say adopted in the Dirac notation. So this is the tensor product of this. So such a dyad tensor product of a vector and the dual vector. Okay, and a general mixed state is a convex combination of pure states. Okay? Convex combination means that there is a sum with coefficients which are positive. Okay, it can be written at least this, maybe in many different cases, but at least it can be, for example, written if we diagonalize it. We say if we find eigenvalues and eigenvectors of this row. So this is one of the possible forms. Okay. Now, what is really interesting and stems from this linearity of this underlying Hilbert space structure is and the linearity of quantum mechanics as a physical theory, okay, which fulfills such a, I would say, superposition principle, which states mostly that if something is a legitimate state of a system, and psi, say, and phi, another vector, is also a legitimate state of a system. So linear combination of them is also a legitimate state of a system. This is this linear, I would say, feature of quantum theory. So as a consequence, one can say that when we consider the system which consists of many subsystems, say n, but at least two, so there are states which are linear combinations of such product states. So, for example, if we have two systems which consist of two subsystems, so each subsystem can be some state, okay? So the common state of the subsystem is the product state of the two. But another legitimate state with the product of some other vectors from this and this space is also a legitimate state. So, and linear combination of them is linear state. So, as a result, the structure which underlies the composite systems is tensor product of Hilbert spaces of the individual system. Okay, in the following we'll assume that all these H are the same. So more or less it means that we consider a system consisting of subsystems which are in a sense similar, the same, okay? So for example, many electron systems or many, I don't know, many atom systems or whatever, okay? And there is a natural division of the class of the states of composite systems into that which are simply and tensor products, okay, of the individual states, and those which cannot be written as a product, okay. So on this level of Hilbert space, on this linear level, this is a separable state or product state, and a mixed and a entangled or correlated state or non-separable state is a state which cannot be written in this form. It must be written as a superpose or combination of such states. Okay, so a mix. Okay, so these are for pure states and mixed state. We can also divide the set of density states or mixed states into two classes. So these which are separable and these which are not. Okay, and a mixed state is by definition a separable if it is a convex combination of pure separable state. So now in this nice notation with projection operators, it could be written in this way with these pi's larger than 0 and summing up to 1. Okay, this is the definition of the. As you know, probably they have very interesting features, this correlated or entangled states, which can be used in quantum information devices, okay, to enhance their properties, for example, to enhance the possibility of sending information and so on. I will not go into details. This is physics, and I will concentrate on geometry. Okay. Okay. So now, when we have such a state of two, I will concentrate here for a moment on two subsystems, but this can be easily generalized to a larger number of systems. So when we have such a state of a composite system that contains the whole information about the whole system, and now we want to learn something about subsystems, okay? And to this end, we define the reduced density matrices, which is simply somehow forgetting about the state of the partner system by tracing out, by tracing it out, okay? So for example, for two-particle system, this partial trace, as you know, is transformation from the linear space of linear operators on H into linear space of one of the subsystem. This is a simple formula, okay, which is then extended by linearity to the whole set of states, okay? Okay, so from the definition of this entanglement, in a sense, it is clear that this maybe not as clear, but somehow this is this properties of the entangled states which are really useful or interesting for the transformations of information, okay, for transporting, transferring, or changing the information. It is clear that these properties should be independent on the, I would say, or not chosen systems of coordinates in essence, okay? Which means that that these properties which are interesting for us, for example, something which we can call amount of entanglement, is independent on the, so is invariant with respect to local unitary action. So if I change something in one system, okay, I cannot influence the properties, the entanglement properties of the whole system, okay? So the natural group which is of interest here is a group of unitary transformation, which is a product of the local unitary group, special unitary group, because the phase does not play a role here, okay? So in a sense, we can say that our goal will be to find interesting properties of the sets of states which are invariant under action of such a group. There is another group action which is of interest. So this group consists of performing such a pure quantum transformations in each system. Okay, we can, for example, manipulate with the fields if these are spin system, manipulate the local magnetic fields and so on. These are the usual unitary transformations made on a system governed by, in a sense, Schrödinger equation. Okay, so but there is another class of interesting transformations which simply consist of doing the following thing. So let's assume that our subsystems are different, for example, distant laboratories, and then people operating these laboratories can communicate via some telephone lines, okay? And they do the following sequence of experiments. They do some quantum mechanical transformation on on their own subsystems, then communicate to the other partners, and so on, and repeat this many times, okay? It can be shown that the relevant group, in this case, which somehow should not change the entanglement properties, is such a group. This is a special linear group, and is the dimensionality of the space, special linear group, okay? So these are transformations which are not singular, simply, okay? And special, so Yes. So phase is once again not important. Okay. So the following problems, we are faced with following problems, which I want to somehow briefly describe during these 2 lectures. Okay. So using equivalence under local transformation. Okay. So this we will call local transformation. So define something which could be useful measure of entanglement. So I would say the quantity of entanglement contained in such a state. Okay, and as I argued, this amount should be independent should be invariant under this local transformations. Okay. So there is another story which maybe I will spend some time on telling you about that. Depends on time. Okay. That, as you know, that there is some very, I would say, quantum mechanical property of being identical, which is completely, I would say, not easy to understand at the classical level. On the classical level, actually, there are not 2 identical systems. Okay, if we can say that this is this system and this is this system and they are the same, it is not true, because they should differ somehow one from another to say at least that they are different. Okay, that they are this. Okay, so although we use in common language the notion of identity on the classical level, it really has a very deep meaning only on quantum level, because, as you know, this identical subsystems or 2 electrons are really indistinguishable. So it means it somehow gives some restriction, puts some restriction on the possible forms of state vectors. Okay, so that must be anti-symmetric or symmetric, depending on the properties, physical properties of this subsystem. Particles, say, whether they are fermions or bosons, and then the structure, this linear structure which underlies this quantum mechanics is a little bit different, because we are now restricted to some subspaces of the Hilbert space, either fully anti-symmetrical or fully symmetrical space. And this influences also this idea of entanglement. And this is, so this is this book. Then it would be nice also, you know, probably that it is not always possible, to reconstruct the entangled state of the full system upon measurements of the made on the subsystems. Okay. Okay. So let me go to some small detour, which will be the, I would say, introduction to symplectic geometry, which I will use further in quantum mechanical setting. But let me remind you something which is probably very familiar to you. So, classical mechanics. So in classical mechanics, I would say the problem is always to determine the trajectories of a system, okay, which is described in terms of some phase variables, for example, positions and momenta. And once we know what are the forces acting in the system, okay? So this is, it means that we have to solve Newton's equations of motion, okay? So in more geometric formulation, it is so that we have something which is called phase space, and phase space is exactly this manifold, okay, which is parameterized by these phase variables, for example, positions and momenta. And then we know forces, okay? And then on this manifold, we have a system of differential equations which allows us to calculate the changes of the positions, okay, of this phase variables. This x are not positions, but the set of positions and momenta, okay? This is a, say, if we have n degrees of freedom, so this manifold is 2n dimensional because it involves, so it is parameterized by positions and momenta. And at each point of this manifold, we have attached a vector, and this vector is the vector of forces, okay, acting on this in this point, okay. So what we are looking for is trajectory. So this solution, okay, which I have written here as a something like that. So it means that this is a curve parameterized by time, and this is the trajectory going through some x. So this equation could be rewritten in this form. Okay. And now we can put this in very nice frames of symplectic geometry. And symplectic geometry is, I would say, a part of differential geometry. As usual in differential geometry, we impose some additional structures on our manifolds. And this is also true here. So we have this differentiable manifold, and this imposed structure is a symplectic form, which is which will be called omega. This is a two form, which is closed, so its external derivative vanishes, and it's non-degenerate. So it means that it vanishes for all at some x for all y. So it is this x, this vector x must be 0. Okay. So this form omega can be used to define something which is, I would say, very important in Hamiltonian formulation of classical mechanics, so the Poisson bracket. And the Poisson bracket is an operation which we perform on two functions defined on this manifold, and to obtain another function. Okay, and it is defined in terms of this omega in this way. Okay. Okay. So it is easy to check that this Poisson bracket is linear in both arguments because omega is a two form, which is antisymmetric because yes, this is a two form, and it fulfills the two identities. One which is called Leibniz rule, which is called because it reminds a rule for differentiation of a product, and the third one, which is called Jacobi identity, which stems from the fact that the omega is closed. Okay. Now, what is the symplectic setting for classical mechanics? Namely, we define the Hamiltonian vector field. In Hamiltonian mechanics, we have a function, which is a Hamilton function, and which is, okay, something which is imposed by the physics, okay, on the system. So it's simply, generally, it is expression of energy in terms of phase variables, so this coordinates and momenta. And for this function, we define a vector field defined in this way, okay, so that the derivative of this, or differential rather, of this age, of our Hamilton function is the action of omega on this field. So this is the definition of this field. Okay, you have to solve equations, write this in coordinates, and you can solve this equation for xh. Okay, this is clearly one form, and this is also one form because it is two form applied to one vector field. Okay, so now our Newton's equations, or in this form, these are other kind of Hamilton equations, have this form, and when we apply the definition of Poisson brackets I've just given on the previous transparency, it is easy to show that this is the proper equation, dynamical equation in this case. Once more, remember that this x is a coordinate on this phase space, so this two n-dimensional manifold parameterized by momenta and positions. Okay, so this is two n-dimensional vector, and this is Poisson bracket with, so it should be written component-wise. Okay, so okay. So it means for each coordinate you have such an equation. Okay. Let me maybe for a moment come back to this picture of say Hamiltonian dynamics. We have manifold, and we have a kind of flow defined by the vector field, which is the vector of these forces. Okay, which stem from the Hamilton function, the Hamilton formulation, but in general this is so. Okay, and now go to this, what I wanted to tell you. So now consider the situation when on the same manifold acts for some reasons. This could be symmetry or something like, but let's consider completely abstract action of a group. And the only restriction is that this group somehow preserves this symplectic structure. So this omega is not changed by this action of the group. This is in mechanics usually called a canonical transformation, okay? Because the net result is that Poisson brackets are untouched by this change, okay? So motion itself, as you know, is a canonical transformation, okay? But let's consider a group of such transformation with this only restriction that each action of each element of the group conserves this omega. Okay, this is formally written, so then this pullback of this omega is omega. Okay, this is the action of the group. Okay, this is the element of the group. This is the coordinate, and this goes to another point. Okay. Let's now consider the Lie algebra of this group, okay? And by this K star, Gothic K star, the dual. So the dual space to this linear space, the Lie algebra is by itself a linear space, and this is the dual space to this. So the space of linear operations which are performed on this space of Lie algebra. Okay. So for each element of the algebra, we define a vector field, which is a so-called fundamental vector field, which is constructed in very simple way. So this Lie algebra element give rise to a one-dimensional action of the group. So it means that if you exponentiate this Lie algebra element, okay, and with time, like that, okay, remember that this is the action of the group. So x of xi is an element of the group. This is exponentiation of this Lie algebra element. And we calculate the derivative of this action at t equals 0, we obtain some vector, okay? Some vector which is tangent to the this flow induced by this group transformation, this one parameter group of transformations generated by this Lie algebra element. Okay, so now you see that the picture is very similar to the previous one. We have some streamlines, some flow lines, okay, which are the lines along which this one parameter unitary group acts, one parameter unitary group generated by the particular element of Lie algebra. And these are these lines, okay? So the group, this one parameter groups, moves the points along these lines, okay? And we defined a vector which is tangent to this line, in a sense, which in a sense, okay, gives speed of this unitary group transformation, okay? So this is like exactly like in mechanical setting I presented before, when this psi was substituted by the capital X, which was a vector of forces, okay, which acted forces in quotation mark, which acted in this way. Okay, so this analogy, in a sense, puts some natural question, okay? So, if the situation is so similar, so can we formulate this dynamics, in quotation marks, induced by this one-dimensional, one-parameter unitary group as a kind of Hamiltonian flow on the same manifold, just like in classical mechanics, okay? And to this end, we have to perform some construction. And this is the following. So first, we define a Hamiltonian vector field. This is the field which, so that along, if we transform with this lines which are somehow tangent to this vector field, our omega it will not change, so it means that the Lie derivative of omega formally vanishes. So there is a famous Cartan formula which expresses Lie derivative of the form in the form of its differential and itself, okay? So we denote by such a Ix the action of arbitrary form on our vector field, okay? Omega is closed from the very definition of symplectic form, so this the omega is equal to 0. So this, because this is 0 from the definition of Hamiltonian field, so we see that this is equal to 0. So the one form omega x is closed. So if the rank homology group of M vanishes, which is a topological, I would say, condition, which means that there are no holes in this manifold. This is a nice manifold, okay, without going into details, okay? But it means that there are no holes, for example. So you know, so that you can, by inverting Poincaré lemma, you can find a function that the derivative of this function, the differential of this function, is exactly one form you are looking for, okay? So this is this one form, and then there exists such a function, then this omega acting on our vector field, this Hamiltonian vector fields, is the differential of f. Okay. So, so now let's remember that this psi hat was this fundamental vector field. So this was the field of vectors which were tangent to these lines of flow induced by this one parameter unitary group. It happens that the proof is not very complicated, but that the function can be chosen to be linear in this. It depends on the Lie algebra element we have chosen, which induced this one parameter flow. Okay. Now, this function mu psi can be chosen to be linear in this Lie algebra element. So it means that this can be written as an action of some dual space element on our psi. Okay, remember that this K star is the space of linear operators on our Lie algebra, on the space of Lie algebra. Okay, so this is the pairing between the two. So it's how it acts. Okay, and the map mu, this map mu, which now takes the point from the our manifold, our phase space, to this particular element of dual of the algebra is called the momentum map. The name is not accidental because when you take a very mundane problem of the rotation group which acts on the manifold, so then this function is simply the momentum connected with the rotation. Okay. Okay, and this mu, as you can imagine, because it defines, in a sense, so this plays a role, this mu which we constructed, plays a role on the Hamilton function for the mechanical system, okay? So remember that for the mechanical system, from the Hamilton function, we obtained Hamilton vector field, which was the field which of tangent vectors to the trajectories. And this mu is this looked for Hamiltonian, quotation mark, for this motion, okay? Because this psi of x is from the construction this, okay? So, in this way, we put this action of one parameter unitary groups in form of a Hamilton action of our manifold, and our Hamiltonian for this action is this map, in a sense, okay? This mu of x actually is the function. Okay, so let me go to a little bit more involved problem, namely so-called actions of the group on its own Lie algebra. There is a natural action of each group on its algebra, of this Lie algebra, which is written here, okay? So this is something which is very familiar to you. If you have a group, for example, unitary group, you can rotate by this unitary group an element of Lie algebra, okay? So this is, for example, rotation of the spin operator, okay? This is U times this operator, say, sigma matrix times U dagger, in this case, U to minus 1. So this is a natural action which can be defined and for each Lie group and Lie algebra. And it can be written in this way, okay? So you simply take this one parameter group generated by this Lie algebra element and then differentiate this action at t equals 0, okay? And there is a, I would say, very natural concept of a dual action, which is simply the dualization of that. So this at star acts as at with g2 minus 1 on the right-hand side, okay? So the action on the form corresponds to action on the vector itself, okay? This dual vector. Okay. Now, what is also important, this construction of this momentum map, this momentum, in this case, for this adjoint, for this group action, can be chosen to be equivariant. It is also a simple proof, but somehow taking some one page, maybe half a page, so that you can be chosen in a so-called equivariant way. So if you act with this momentum on some point, which is the shifted point by group action generated by this G. And this is the same as acting with adjoint action on this point mu of x. Okay? It happens that on this coadjoint orbits, so this orbits of this action, okay, so this is a set of all points generated by all elements of this group. Okay, there exists a natural symplectic structure, which is called constant Fourier form, and it is defined here. So let this x, I don't know why it is capital X here, but okay. And this is the vector tangent to this curve, okay? So this is also one parameter action, okay, generated by this x. So we define the symplectic form of these two vectors simply by commutator of the fields. Okay. Okay, and this I think is the very good point to end today's lecture. And then this is the anticipation of what will be the next point. So we'll finally come back to quantum mechanics. Okay, and now maybe there are some questions.
You mentioned that this mu, you can choose it linear. Okay, so that means putting some constant to 0.
Yeah.
Okay, but that's about the only freedom you have in...
That's true.
But then if there was a second, you can choose it to be equivariant. So where does this extra freedom come from?
Okay, so no, it's more freedom. It's not only that it can be put linear, it can be equivariant. This I have to think about that, but there is a simple proof. You have to, it also depends a little bit on the structure of cohomologies of the manifold. But yes, so probably I should assume something about cohomologies.
Okay, okay, thanks.
Thank you. And if the first cohomology group of the RAM is not vanishing, there is a way to define something like a momentum map.
If it does not vanish, yes? If it does not
Yes.
vanish. Yes, but it will be somehow not functioning in the way I'm intended to do so. So it's probably so that there were some. I cannot answer this immediately. What will be wrong? But no. In the general question, the general answer is no. Okay, there's some special cases which you can consider.
In
But
that case, it won't be something like Hamiltonian. If that
yes,
exists, it will be something
yes,
far
yes,
from
yes,
Hamiltonian.
yes. Mhm.
Hey, but for compact manifolds, this first homology group always vanish, right? For
So cohomology group for compact groups. Yes, yes,
Yeah.
yes, yes.
okay, and well then, for example, for the projective space, we will never have a problem of this
Yes, in
equivariance.
principle, yes.
Okay.
So in our case, there will be no problems with connected with this. Okay. Okay, so I think I'm in time.
¿Cómo se mueve? ¿Cuál es? Control L. Ajá. Okay. Muy bien.
So the second lecture will be by Andrei Klimov. We will give a lecture titled Classical Hamiltonian System, Geometric Input and
No,
Harmonic
no, no, no,
Analysis.
no. This is not. This is
That's a
just
section,
this
yeah.
slide.
Yeah. So he will give a lecture, the first slide of which was that, and then the title is Quasidistribution Functions on Homogeneous Phase Spaces.
Hello. Good morning. Thanks for coming. So I have prepared 2 classes. Actually, I made a big effort. So in each class, I basically put a whole semester of teaching. So please don't pay attention to all equations you will see. Don't write anything. I think Chris will later upload the presentation. And let's fix us only important equations. I will try to point here. And this is a short introduction on the physical level, no mathematics here, I mean not tough mathematics, to the theory of quasi-distribution function and phase space method for continuous system. If somebody will stay with me tomorrow, so we'll use some of information you will hear the day tomorrow. So let's start with the class. And it is, although it is not truth, but it is nice. So it's a lot of equations. Please don't pay attention to all of them. So it is not truth, but it is nice to think that phase space methods originated from the idea of quantization Hamiltonian system, which we associate with a symplectic manifold equipped with a Poisson structure. And Marek actually gave a good introduction to it. And in this Hamiltonian symplectic manifold, we have several tools given for free. And one of those is the set of harmonic functions, which are eigenfunction of Laplace-Beltrami operator on the manifold and some appropriately commuting vector fields. And these set of harmonic function, they are orthogonal, and most importantly, they complete a full basis. So they resolve the identity in the sense that we can construct out of harmonic function the so-called reproduction kernel on the manifold, in the sense that integrating with this kernel, we can go to any point of the manifold. So this guy will play a lot of, will be very important for us. So please check it out and see it again. We have set of harmonic function. They complete a basis on the manifold, and they resolve the identity. In addition, the next tool given for free for symplectic manifold is the possibility to describe the manifold in terms of, in the ambient space, in terms of block vectors, which also has a very close connection to the phase space method, actually. Now, the quantization idea originated by Dirac was kind of naive in the sense that we want to put in correspondence classical observables with some operators acting in a Hilbert space. So in such a way that in some limit, the Poisson bracket and the commutator of the corresponding operators can be related to a certain manner. This method, we know it fails. It fails very quickly, it doesn't work well, and instead of looking for such an impossible map proposed by Dirac, the humanity found several ways of quantization. One of those in particular, Marek came very close to the Kirillov orbit quantization method, but we'll, since we're interested in the phase space method, we'll focus on the so-called Weil-Moell strategy, which allows us to quantize systems which are subjected by certain condition. So we have a manifold, but not only manifold but as itself. But we know that in this symplectic manifold, there is a group which acts transitively, which means transitively means that by group action, we can transform any point of manifold to any other point. And this is it, basically. So we are looking for the map which allows us transform in a simple way any function, any smooth function on the manifold, such as symplectic manifold, to an operator. And then we'll have a possibility to go back and dequantize. So go from the operator back to the classical observables. So this, it results that such a strategy can be implemented by so-called Stratonovich-Weil map. So the idea of such a map is introduce a mapping kernel between two different objects. One of those are functions on the manifold, and another one operators in a Hilbert space. But these two structures, they are related between each other. So they are not independent in the following sense. So what we have? First, we have a system. Suppose we can, it is easy to start from the quantum point of view. So we have a group, we have a quantum system, and which possess a symmetry group, G, which acts in the Hilbert space. And then we find some appropriate subgroup. It is not important for us how, appropriate subgroup, and we construct a manifold, which is a quotient of the group of a subgroup. So we have a structure which consists quantum system, say quantum system, group, symmetry group of the quantum system, and symplectic manifold constructed out of this group. And then one can introduce a map. So the map is through this quantizer or quantizer kernel, Stratanovich-Weil kernel, which from one point of view is an operator acting in this Hilbert space, and from the other point of view, it depends on the point on these manifolds. So the map from the operator, map from the classical observable to the operator goes through by the integration of this function with this kernel, and the inverse map, the dequantization process, goes from comes from tracing this kernel with this operator. So this classical symbol is just the same as a function on the manifold. And to construct such a kernel, we impose, by axiomatically impose, some physically transparent conditions. The most important condition is the covariance. What does mean covariance? What we want from this map? Basically, we want the following. There are some equations here. But we want the following. If we have an operator and we map it to some function, and then we transform the operator by the group representation operators, so we obtain something else. So this something else, it is not completely different stuff, but it is the same that we had initially, just shifted to another point of manifold. So the idea of such a map, here is a map from the operator space to the function space, is preserving, is shape preserving. So such a shape preserving here is in this covariance condition. The other condition should give us the possibility to manipulate with the symbols of operator in the same way as we manipulate from the operators. So we do not lose anything in this map, in the sense that if we want to compute, for instance, trace of two operators, we can do it through, we can compute trace of two operators. We can do it through integrating classical images of such an operator. I hope this is more or less clear. Yes? Yeah? Yes. Good. So you can ask any question anytime, please. Especially if there are people which are completely unfamiliar, so maybe it is too tough, maybe I go too fast. But anyways, this is for advanced postdocs and PhD students. So this condition, which allows us to manipulate with symbols, with classical functions, in the same way as their corresponding operators, is called traciality. There are a couple of other conditions which basically preserve the property of operators on the level of its symbols. For instance, if I look for an image of a Hermitian operator, I will get a real function. So this is a reality condition. This is not that very important. But these two conditions, covariance and traciality, are really important because they allow us to work with symbols and operators in the equivalent, completely equivalent way. So this is not the whole story. There's a problem, and the problem that if we implement this or any other kind of quantization process or dequantization process, so this is quantization process, then it results, there are several classical possibilities which has the same quantum map. So several quantum functions can be mapped into the same operator. So in order to distinguish such maps, it was introduced not a single map, but a class of maps. And we'll consider one particular class of maps which contains, which everybody knows, the concept of coherent states. There are different possibilities to generate such map, quantization, dequantization. But we will focus only one specific type of maps. So it is usually called S-parameterized family. And the correspondence between classical functions and the operator in the Hilbert space is through the kernel, which depends not only on the phase space point, but also on some additional parameter. So when we vary this parameter, we can achieve different maps to the classical manifold, although the quantum operator is just the same. So there are some equations which are really not important for here. Okay, well, as I said, the main tool which we will use here is the concept of coherent state. So everybody knows what coherent state. So we choose in the Hilbert space, we choose some fiducial state, we apply the group operator, and the orbit of such a state and the action of the representation of the group basically is a set of coherent states. I think everybody knows what is this. This coherent states has a couple of trivial properties. Everybody knows that such coherent state, they are covariant under group transformation, they form an overcomplete system, and in addition, there are two properties which are not that common in books, that we can generate those Bloch vectors we told which are used for description of the manifold from the point of ambient space as an average value of the group generators over coherent states, and the adjoint action of the commutator of the group generators with the projectors on the coherent states. It's just an application, can be easily reduced to the application of vector fields. Recall these vector fields which commute with Laplace-Beltrami operator, action of the vector fields on the projector on the commuter space. What is the important point here? It is not this, which you can find in any book, but something else. Recall that we have this important construction, which is reproducing kernel on the manifold. Basically, it is a kind of delta functions, not completely delta function because it may depend on the group representation. It is a kind of delta function on the manifold. So actually, and it results that there is a connection between two apparently very different constructions. One of those is this reconstructed kernel, and another one is a squared overlap of two coherent states. It results that these two apparently very different things can be related through an operator which depends only on the Laplace-Beltrami operator on the manifold. So this is a kind of smoothening process because this is a sort of delta function and this is a kind of, everybody knows, kind of Q function, something smooth. It is always something very smooth. I mean, at least for the group we consider. So this smoothing relations plays the super important role on the quasi-distribution levels. So what does it mean? Since it is very important, let's make a very short calculations. So phi are the harmonic functions. If we sum the harmonic function over index corresponding to the eigenvalue of the precisely vector fields, we'll get the so-called zonal spherical harmonics. Do we know this? Anybody knows? It's a bit about group theory. Zonal spherical harmonics. In case of SU2, what would be? Somebody knows? So maybe I'm just talking to the vacuum, and we just stop now, and let's go to the questions directly. So when we sum two spherical harmonics over M, what we have? Legendre polynomial. This is zonal function. No? Well. So, well, so this reproduction kernel on the manifold is just the sum of zonal spherical harmonics. So then this equation, which we know this, it came from spherical harmonics. We know this, it came from coherent states, group theory. So how to find this operator? So to find this operator, we just expand the reproduction kernel on the spherical harmonic, apply this operator, and since it depends only the Laplace-Beltrami operator, so we end up to this kind of equation. So known thing, unknown. So if we are able to invert this equation, we find this spectral function, which are eigenfunctions of this smoothing operator into words. If anybody wants, you could later take a calculations and go through these notes. So this smoothing relations is absolutely basic for the quasi-distribution theory. Well, now, particular cases of such as parametrized maps. Everybody knows Q function probably, right? There's a Husimi symbol, which came from averaging the operator over the set of coherent states. So the kernel is very simple, is a projector on the coherent states. Glauber, covariant sim, Glauber, Sudarshan map, which came from expansion of the operator over the coherent state projectors. So here, the coefficient is the famous P function, everybody knows. But we don't know what is the form of the kernel here. It is complicated, it's more complicated than this one. And these two functions, Q and P, are related precisely through this smoothing relation. So we integrate the P function, which we know always has a kind of not very good shape, or it may have not very good shape, kind of singularity may be present there. We integrate it with the overlap of two coherent states. And probably the most interesting in physics in applications is a Wigner map. This Wigner map is the most, in sense, most close to the classical one, since it is so-called self-dual. In what sense? How we compute average value statistical physics? We integrate the distribution function with the distribution corresponding to some observables. So we integrate something with something of the same nature. So self-dual means in order to compute a trace of two operators, we integrate the Wigner function of these two operators. We integrate the product of Wigner symbols, of the same symbols, and this is very important. So such a map really is different and possess many important properties. How many time do I have? 11:15. So I have 45 minutes basically. As I said, I can stop any moment. If you wish just like Teflon, we understand nothing. So, well, all these maps can be unified in this so-called S-parametrized family. And the common way to represent the kernel of such parameterized family is through so-called explicitly covariant form. Recall what means covariant. We move something, and this something does not change shape. It's the same up to the group action. So covariant form of the kernel means that we have the map at 0, and this map at 0 we just translate through the application of group representation operators. So this is called explicitly covariant form of the mapping kernel. Well, this is semi-sim group, let's skip it. Well, now, a bit non-trivial point here, maybe not that common, even for maybe who worked with the phase-space method, is the following. So let's recall, we have Q function and P functions. They're related through the smoothing by integrating with the overlap of two coherent states. Smoothing action. So the same relation is for the mapping kernel, of course. Now let's recall that this overlap can be obtained as application of this special F function of the Laplace-Beltrami operator, which is very important. So it is an invariant function on the manifold, applying to the reproducing kernel. What is reproducing kernel? Delta function on the manifold. We just take this and substitute here. What we can do? This operator acts as a self-dual stuff, so we can basically take it out from the integration and integrate the P function or the corresponding kernel with the delta kernel. What do we have? The kernel. So what does it mean? That these two kernels are related through the integral action, or they are related through the action of the operator of Laplace-Beltrami operator. So this is kind of smoothing action on the operator level. So in general, any map, not only one P and Q kernel can be related in this way, but any S-parameterized family can be tied up through the action of such an invariant operator. So if I somehow compute Quasidistribution, classical image of some operator corresponding to any value of S, I can immediately obtain any other S by applying some operator. Well, okay, a lot of equations. Now, this is the line here is not that known. So let's discuss a bit. So we know these two tools we have. One tool came from a symplectic manifold. What is this? The basis of spherical function. Another tool comes from Hilbert space. What is this? Projector to the coherent states. They form an overcomplete set. So now we can construct these are called irreducible tensor operators. This is the same tensor operators you work in the standard angular momentum theory. So integrating these two guys, we have something which is transformed under group representation in the proper way, which is very nice. So why it is nice? Because this is a covariant basis in the space of operator. Any operator you have can be decomposed in a linear composition, in a linear form of such tensor operators. Interesting point here. So this is how we connect two different concepts. So they're not really independent. They have the same origin. This is the very important point. And even more interesting, so here we have a coefficient, and it results that these coefficients, which is very important by the way, it is average is proportional to the average value of these tensor operators trivially, but interesting that it is proportional to the power of the spectral function, which precisely transform the reproducing kernel on the manifold to the overlap of two coherent states. So everything here is connected in a single equation. And since these operators, they form a covariant basis in the space of operators, so we can decompose any operator in the sum of those. In particular, what we can decompose are the quantizer kernel. And any quantizer kernel has this form. So it is a basis in the space of operator, basis in the space of function. Why? Because the kernel depends on the point of the manifold, and this guy, which allows us to move in the space of different S. So to move from Q, P to Wigner function by changing just the power of this invariant. Here is the spectral function, but actually it is invariant. It is invariant operator. So it is more or less the general stuff is up. Let's analyze a few special cases. So what do we have? We have this absolutely strange S family of quasi-distribution. We can divide it into 3 unequivalent parts. One part corresponds to the negative value of S. These are kind of classical-like map. They tend to be similar to something smooth. There is a non-classical kind of map, which corresponds to the positive value of S, P functions. And as a special comes the Wigner function, which is self-dual function. Actually, if anybody knows about non-classical depth? No? Okay, then we'll skip it. There is a strange term which came from Heisbeck-Weil, flat phase space, non-classical depth, which has nothing to do with non-classicality, but it basically says us how we can smooth something which is not smooth, and it is some kind of good classical function. So, but we'll skip it. Now let's go to the examples. Everybody likes to see what he knows. So everybody knows the flat space Heisbeck-Weil group. So what we have here, the manifold is a complex plane. What we have there are the harmonic functions, resolution of identity. Here our reproductive kernel, displacement operator, action of the group representation on the Hilbert space, average value of the displacement operator. What is average value of displacement operator? Harmonic function multiplied by something. This something is not occasional here. It is not strange stuff. This is just a smoothening of delta function on the manifold, because the invariant function is exponential of a second order derivative. So it is. So what we have here, it is not something casual. It came from the general theory. It came from the spectral function. So we can we can move in the space of quasi-distribution as we want by applying this kind of operator. This is special kind. This group has a special position in all this group theory, because we like to work with semi-simple groups where everything is clear, nice, and this group is not semi-simple, but still most of things we can do for semi-simple group we can apply here. Well, properties, everybody knows properties. Q function is smoothing of Wigner function. We can smooth it. I think here 2 is not good. So this equation has very important property, which are particular to this group. We relate Q function and Wigner function through the smoothing operation. So if Q function has zeros, we know that it is always non-negative, but it may have zeros. If it has 0, this means the Wigner function is negative. a negative Wigner function we kind of associate with something non-classical. It's also not very good notion, but still. And many people use the concept of negativity as an indicator of non-classicality in the Hilbert space. Very important, very important. The only Wigner function possess so-called tomographic property, absolutely non-trivial property, which is proper only for the Wigner, for the self-dual map, which means the following. If we have a Wigner function of some state and integrate it along some line in phase space, what we have is a density probability of projecting the state into the eigenstate of the operator, eigenstate of the operator corresponding to the rotation in the phase space. So Q is the eigenstate of the X operator. So with this phase space rotation, we do like this. So this eigenstate is precisely correspond to this line in the flat phase space. So this tomographic property is extremely important in applications, and it is done basically only for the phase for flat space. There are some other theorems called very famous property that the just escaped my mind. What is this name? Entropy, thanks. So the so-called well entropy is minimized for the coherent states. And there is a very famous also Hudson theorem saying that only applied to pure states, the non-negative Wigner function can be attained only for pure Gaussian states. This pure state has non-negative Wigner function, only this Gaussian. So this is important property which also allows us kind of manipulate non-classicality and classicality, which is good. And for compact group, for instance, this is not true. Okay. Another time. Okay, so we have plenty of time to fill our brain with garbage. So SU2 case, also very simple. Everybody knows what we have. We have a manifold which is just a two-sphere Bloch vector. Recall the Bloch vector is average over group generates over coherent states. Coherent state, everybody knows how they're generated. And we have this harmonic function, eigenfunction of the Laplace-Beltrami operator. Resolution identity. This is reproduction kernel, which is a sum over harmonic functions. So here precisely the Legendre function weight appears. And what we construct out of the general composition, again, without thinking, this is a good kind of sign of science. So when we can do something without thinking, but just following the certain procedure. So we can construct irreducible tensor operators. How? Coupling, here it should be conjugated. Coupling the harmonic function, projector, and this guy here, we know from the Varshalovich or any other book, we know what the form has the irreducible tensor operator. But now we understand what is this guy here. This guy here is average of the tensor operator over the fiducial state which we use for the construction of the coherent state. And in addition, we know also that this guy is a square root of the spectral function, which is used for transforming overlap, the reproduction kernel to the overlap. So for instance, how we can find this function here. We don't find function, we find its spectral image, of course, so the spectral function. So we apply, as we already seen, we apply this guy to the delta function, so we have this equation. And this equation is fulfilled for the precisely our spectral function. So everything, again, is self-contained. Everything is tied up. Harmonic functions, coherent states, smoothing relation. Well, then we can construct the mapping kernel, which allows us to construct any kind of quasi-distribution functions in a very simple way. We know the procedure. Tensor operator, harmonic functions, spectral function. This is good. Interesting. We know what this kernel has, for instance, for the S equal to -1, correspond to the Q map, and just projected to coherent state. And this is precisely the condition we established from the beginning. We said that we choose a very specific type of map where coherent state would participate. So here's a participation. Then it is also interesting to observe, if we go back to the Heisenberg Y case, then the Wigner kernel at 0, because recall that this map at any point can be moved to 0, and any other kernel is obtained by just a group transformation of the kernel at 0. So a kernel at 0 has a form of a parity operator. I think we didn't stop here. So, and this is a very important property, which actually allows us to construct all kind of well-cited tomographic reconstruction form, and which can be actually experimentally implemented. Precisely this property. So in case of SU2 group, the Wigner function does not have form of delta function even in the manifold. It tends to the parity on the sphere, but only in the limit of large dimension of representation. And even this approximation is more or less good only for this kind of localized, so-called localized state. In general, it is not good. It is not truth. It is not truth. Even in this limit, it is not really truth. For instance, what is the form of the Wigner function of coherent state? We already see, everybody knows, Wigner function of the coherent state in case of flat. It is just a Gaussian. Everybody knows this. What is the form of the coherence of the Wigner function for the coherent state? Is, as we understood, this is the most important guy, Wigner function. It has some kind of complicated sum of Legendre polynomial with strange square roots. However, in the limit of large dimension of representation, limit of large spin, basically, it tends to the exponential form, to the Gaussian form at some point, but modulated by this Bessel function. So we cannot escape from this Bessel function. It is would not be good normalized. Now, we already seen that for the compact manifold, reproducing kernel is not a real delta function. It depends on the representation index. And this means that we cannot apply strictly none of the properties we usually manipulate for the flat phase space, for the Heisenberg group, to the compact group. So it is not true for SU2, it is not true for SU3, it is not true for compact semi-simple group. So we don't expect Hudson theorem in any sense. There is no such thing as, say, Gaussian states. So we can introduce kind of Gaussian states, but they will be always kind of Gaussian state, because all Wigner function of even coherent state would have negative region always. It would be small in the limit of large spin, but it is, what else? Q function has 0. In case of Heisenberg well, Q function, they It does not have zeros in case of Heisenberg, while now it has zeros, and actually this is a kind of interesting classification through Majorana stars and so-called. Maybe everybody, at least students of Chris probably knows about this. Yes. Here? This one? It has zeros, yes. Q function has zeros. It could have zeros, yes. Q function of for the SU2 has zeros, yes. Actually, as a single generated zero. Single zeros. Yes, the antipode, yes, it has zero. It has a single, has a single generated zero. It has zeros in the sense that there's a single zero which is twice degenerated, yes. And yeah, more interesting example, less trivial. SU11 a group, for SU1 group, the symplectic manifold is hyperbolic. It is an upper part of the two of the hyperboloid, and the coherent states can be constructed. We know maybe somebody knows that SU11 group is not that trivial as is SU2. Has different kind of representations. So the coherent state we usually construct for physical applications is for the positive discrete series, and they're constructed by application of displacement operator to the fundamental state. However, we cannot define a set, a good basis in the discrete representation. We have to go to the continuous representation, to the principal continuous series. And only for continuous series, there is a concept of spherical harmonics. This is maybe a bit difficult to explain. What is the point? For discrete, for compact group, the eigenfunctions, they correspond always to the compact motion. So the spectrum is discrete, right? For the hyperboloid, there are different kind of motion. So general motion, I mean, particle on the hyperboloid, of course it can go anywhere. So its spectrum is continuous. So from on the physical level, it is clear that harmonics comes only from the continuous representation. So these functions are analogs of spherical harmonics on the hyperboloid, and they also resolve the identity. And here, what is interesting, the delta function which appears on the hyperboloid, it is a real delta function on the manifold. It is not like in the compact case. Then, again, constructing tensor operators, same stuff. Coherent states, spherical function, spectral function, with all the same properties. There are some complications. For instance, these tensor operators are not trace class. They have trace infinite. But for instance, they form a complete set, so they are trace orthogonal. And this spectral function can be found. So we can invert the equation we have, which ties the overlap of two coherent states and delta function on the manifold. So it results that this equation can be solved. So we can find spectral function just inverting this equation, which is very nice. It gives us something similar to the Clebsch. For SU2 we had Clebsch, if you remember. There's something similar to Clebsch, but which relates to the coupling of continuous series. Well, what else? Okay, the general form of the mapping kernel, the same. Tensors, harmonics, spectral function. Asymptotic property. Wigner map at 0 tends to the parity on the hyperboloid in the limit, classical limit of large K. K plays the role, because the Barman index plays the role of the representation index for the discrete series. Properties. Coherent states. Q symbol of coherent states. Recall, for Heisenberg case, Q function, they do not have, Q function of coherent state do not have zeros. SU2, it has 0. SU11, it does not have zeros. So Q function on the hyperboloid of the coherent states is something which is positive. The Wigner function of coherent state is always positive. So we have one-way Hudson theorem. So if we have coherent states, the Wigner function is positive. It is not vice versa, but one-way Hudson theorem can be applied. And well, the smoothing relations between Wigner function and Q function is just the same as in the Heisenberg case. So we obtain Q function by smoothing, and since it does not depend in this, it is real. This function is obtained from the real delta function. So it is not like in the SU2 case, where we cannot relate the negativity of the Wigner function and zeros of the Q function. Here we can relate as in the Heisenberg case. So Q function may have zeros only if the Wigner function on some state takes negative values on the hyperboloid. Well, so, sorry? Yes. Yes. We're talking about the upper leaf of the hyperboloid. So the positive, we're talking about positive discrete series. It is there the high coherent states are defined.
Is it related with having odd or even number of?
No.
Because you have also two different.
This is two different. You mean when you talk about kind of boson realization?
Yes.
No, all boson realization corresponds to boson realization when we work with embedding of Heisenberg-wide algebra, squared Heisenberg algebra to the SU11. We have two different representation corresponding to k equal to 1/4 and 3/4. They both correspond to some representation. So here, actually, it can be adapted indirectly. Directly, it is not cannot be adapted, but indirectly, it can be adapted. So I thought about the upper leaf of the hyperboloid because hyperboloid has two leaves. So it is. So the manifold is the same. So let's recall in general what we have. So we have a map from the operator to the function on the manifold. This map is realized through a kernel. This kernel is constructed based basically on the properties of coherent state. The coherent state, so in fact, is indispensable in this sense. And everything can be related to this smoothing condition, how we can go from the delta function on the manifold to the overlap of two coherent states. This actually allows us to move inside this family, QP Wigner family, by application of such a smoothing operator, which is an invariant operator in the manifold. Invariant in what sense? Invariant under group action. So it's a function of the Laplace-Beltrami operator. Well, just for comparison of different groups. So we saw that this group, being non-compact, is quite similar to SU11, and SU2, it is not the same. SU2, SU3, I think I promised also to talk about SU3, but just no space. If somebody wants to know anything, please ask me privately. And this is in a few words what we have in plan of comparison. Do I have time? Like 10 minutes. Okay. Let's go to the interesting physical part, dynamics. which is, the question is, can we use this, we have to understand this kind of big chunk of equations. The question is, what for? Can we really use it somehow? Or it is just kind of, in Spanish would be adorno. Something which very nice, but it is like this elephant you put in your cuisine, a small elephant which is very nice, but only used just to take dust out from it, nothing else. So the question is, so we can use it. There are several several ways to use it. One of the possibility to employ all this construction is to discuss the quantum dynamics. So quantum dynamics means we go from the Heisenberg equation or Schrödinger equation to the equation of motion for the quasi-distribution functions. So it results that once the map from the Hilbert space, from the operators to the manifold is given, we can find the so-called star product. What is star product? It is, sorry, I should have, it is just image of a product of two operators. So I have two operators. I can compute their images. How I can relate these images of two operators with the image of the product. So the image of the product is computed through the so-called star product between images. This star product is a very complicated, in general, it's quite complicated differential operator, which is known, up to my knowledge, only for Heisenberg-Weil SU2 and SU11 groups, nothing else. And having this map from the product to the individual functions, we can go from the Schrödinger equations to the so-called Moyle equations for the quasi-distribution function describing the state. So this is a general form of such equation. This is a very complicated equation. It is impossible to solve, practically impossible to solve it, except for trivial situations when the Hamiltonian, say, is linear on the group operators. It's complicated, just no way to solve it. I mean, it's complicated. However, I'm sure that you studied, at least in some quantum mechanical course, the semi-classical approximation. And this semi-classical approximation, I'm sure that you were told that in XP phase space, XP, say X representation, the expansion parameter is what is the expansion parameter for semi-classical, for quasi-classical approximation? H bar. So this is false, of course. H bar is not a mathematical parameter, but physically it is not a good parameter. Physically, the expansion parameter for XP system, for flat system, it is inverse energy basically accumulated in the system. Inverse energy, and not H bar. H bar, it is not representative because the scale of quantum system depends of its energy and not only of this H bar. So this is, so the point is, as well as understand, maybe I'm not quite well in, I don't know, but the semi-classical approach is the only one which allows us to go smoothly from the purely quantum description for any symmetry group to semi-classical description. Why? Because it results that this Moyle equation can be always expanded on the some physical parameter. Then this physical parameter for different group is different. For instance, for Heisenberg-Weil group, it is inverse energy, inverse number of photons for physical terms. In the for SU2 group, it is an inverse spin size. For SU11 group, it is inverse Bargmann index. It also can be interpreted physically in a sense. So it results, so to the first order, this equation of motion in the phase space can be reduced to the semi-classical equation of motion. And very interestingly, that this complicated stuff mathematically can be reduced to the Poisson brackets plus some quantum correction. And the first order quantum correction depends on this parameterization index S. So the first quantum correction disappears for the Wigner function. This is one of the reasons why we tend to use Wigner function, not Q and P function, to describe the evolution of quantum system. So it's just more precise. And this equation can be solved. Of course, this is trivial equation, linear equation. And the so-called semi-classical approximation solution of this equation is also very simple, which is called semi-classical approximation or truncated Wigner approximation, which basically says at the first order approximation, the quantum dynamics is the following. We have a distribution. This distribution is quantum because quantum state has a form of distribution in phase space. Look at this. And every point of this distribution moves along classical trajectory. So this is very nice semi-classical approximation which allows us to describe the dynamics, quantum dynamics for short times, but describe it quite precisely. Here is an example. Here's an example. This is a numerical example. Under this for SU2 group, under this Hamiltonian, Z square, non-linear Hamiltonian, exactly solvable, but it does not matter. So we can see how the coherent states evolves with time on the sphere, and in comparison, the semi-classical equation. So for short time, this description actually gives quite good correspondence if we want to compute some average values. For larger times, when we have this kind of Schrödinger cat formation, maybe somebody knows what a Schrödinger cat, how we can go to there. So of course, semi-classical approximation does not work. Interestingly, also, that this exact evolution equation can be always on the manifold reduced to the continuity equation. So the derivative is divergence on the manifold of some quantum flow. And in semi-classical approximation, of course, this quantum flow is just classical preserving flow. Well, I think this is it. This is Boop apparatus. Let's skip it if somebody wants. It is quite a kind of 3 minutes? 1 minute. Okay. A couple of just nice pictures. Evolution of coherent states on the sphere, how it evolves. Short times, so it generates this rippling, kind of quantum interference. Longer times generate cats. First 4-component cats, 3-component cats, and finally we get to the 2-component cats, the maximum quantum state in this sense. And this is evolution on the sphere. And this is evolution on the hyperboloid. So this is coherent state. It looks not, look at this. Here coherent state look like, this is not a circle, but it is something like circle put on there. But here it does not, because of the form of hyperboloid. It is not symmetric, up and down. So evolution gives you also something, short time, gives you something like squeezing, but SU11 squeezing. It is not the common squeezing, probably you know. And for longer time, it generates cats, 4-component states. Look at this here. We have super resolution, as they call, and 3-component cats, and then finally 2-component cats. This is very nice picture. And this is when the dynamic is governed by the compact K0 operator. Maybe somebody knows. 1 minute. It's just nice picture. It's difficult to find it in literature. This is why they kind of. So this is a compact operator. It has a discrete spectrum. So evolution is compact, as we can see it here. Compact evolution. It does not go outside. But if the generator is non-compact, then evolution is completely different. So we have initial coherent state. So it starts to spread. And actually, it is known that for this Hamiltonian, there is kind of catastrophe. So at some moment, if you compute average value of K0, at some time, it has singularity. Everybody knows this, no? So average value has singularity, but the Wigner function does not. This is a very interesting point. So thank you very much. I think it was too heavy, and tomorrow it will be even more heavy because I will talk about even less known discrete phase spaces. But if you survive it and take a look later, probably you will understand, we will be able to understand basically, this is a kind of short guide to the Quasidistribution function, basically one semester course you received in 50 minutes. So if the fraction of understanding is small, it is okay. 15% is good. 15% or 50% actually.
Okay, let's thank the speaker, and there is a coffee break now.